Hi guys, welcome to part 4 of the Magnetism series. In this video, we're going to answer the question posed at the end of the last video, which sought to know what the velocity was that a particle has as it enters the magnetic field. In other words, how can I accelerate the particle? We'll seek to answer that question in this video by looking at work and energy from the perspectives of the electric and magnetic fields. We'll also look at other interesting patterns that occur in magnetic fields. And finally, I'll leave you with a challenge to try to see if you can figure out how to manipulate a charged particle in a magnetic field. Let's get into it. All right, so let's take a look at how I would measure this V value in the equation. Now, what I need to do is I need to have the particle already moving by the time it enters the magnetic field. So in other words, I've got to accelerate this particle prior to entering the magnetic field, and I'm going to do that by creating a potential difference. So we could have a structure set up somewhat like this, where in this region, I have a potential difference that would cause, let's say, an electron to accelerate across that potential difference, and then enter through this little gap in the plate. And in this region, I have the magnetic field, and that portion we've already talked about. So in order to calculate the velocity of the moving particle as it's entering the magnetic field, I would actually focus on this prior section over here. So there's more than one way to calculate the velocity in this portion, but I think the easiest is using conservation of energy. Now we know that the work that an electric field can do on a charge is equal to Q times E. So Q is the charge that's moving, E is the strength of the electric field, times delta X, which is just FD. Now I know that E delta X is equal to delta V, so I can see that the amount of work can be calculated, so the amount of work that the electric field is doing, by saying the charge times the potential difference. Now I know that mechanical work also equals a change in kinetic energy. So if the particle starts from rest and it accelerates up to some speed, I could write this expression. Delta K, for the change in kinetic energy, is equal to Q delta V. I can then expand delta K to be 1/2 m times V final minus V initial squared equals Q delta V. Now I know that the V initial is 0, so really what I'm doing is saying 1/2 m V final squared equals Q delta V. And I'm solving for this V final. That will then become the initial speed that it enters the magnetic field with. Just be careful here that you don't mix up this delta V with the V over here, because one is for velocity and the other one is for potential difference or voltage. This is a great way to solve for the velocity because we know that the electric field can do work on charged particles, which is great. Now you may be thinking, all right, that's great. We know the initial velocity of the charged particle as it enters the magnetic field, but what if its velocity changes in the magnetic field? Let's analyze that from the same perspective using work and energy. Let's continue to use an electron here. And now we're focusing on the portion when it enters the magnetic field. So I can see that once it enters the magnetic field, I would use the right-hand rule to calculate its trajectory. And in this case, actually, I would use the left-hand rule. So I would say that it's going to curve to the right, like this, and it's kind of going to spiral in that direction. Now we know from our work function that force is equal to the dot product of F and displacement. That's very important. That means that the force has to be at least somewhat parallel to the displacement or the instantaneous position. Now we know in this case here with magnetism that the magnetic force is always perpendicular to the velocity or the instantaneous position. That means that if we were to try to plug in the magnetic force as the force doing work, we would see that this dot product, which expanded is FMD cosine theta. If I were to plug in 90 degrees for theta, which is the angle between the magnetic force and the particle's velocity in the magnetic field, this would always come out as 0 because the cosine of 90 degrees is 0. So in other words, what this is saying is that the magnetic force cannot do mechanical work on charged particles. Now we also know that work equals a change in kinetic energy, as we just described in the electrical portion. And so if there's no work done, there's no change in kinetic energy. And no change in kinetic energy implies no change in velocity. So even though the direction of the particle is constantly changing because it's moving in a circle, its speed is not changing because the magnetic force cannot do work on it. Now, if I introduce other forces in the magnetic portion of this setup, then sure, I could change the speed. But the magnetic force itself, if the only force acting, will not change the speed of the particle. Now I realize that's a lot of information. It's taking a lot of mechanics that you've learned probably in a first semester course or earlier on in the year, and then having to blend that with this new information to put it together. So I highly recommend reviewing that a few times and really trying to understand and to internalize the idea that the magnetic force cannot do work. This leaves us with a really cool thing that you can achieve with the magnetic force. Now what I'm going to do here is I'm going to construct a magnetic field that's pointing to the right, and I'm going to say if I launch this particle in at an angle, let's make it a positive particle this time, so we'll use the right hand, we see that it's launching in at this angle between the velocity vector and the magnetic field vector. And that means that we are only going to consider this velocity component in order to calculate the magnetic force. Now, only that component is going to contribute to the magnetic force. So what we would see if we're trying to draw the path of this particle in here, now based on the way that I have the magnetic field set up, drawing this path is going to be kind of interesting. So I'm going to use my right hand rule first. I'm going to say that the field lines need to point to the right. My velocity, the perpendicular velocity needs to point straight up. That leaves the magnetic force pointing into the screen or into the plane of the page. Now, if we think about that magnetic force as pointing into the center of a circular path, I will see that my hand has to curve sort of into the page, or my index finger curves down into the page, meaning that the particle's trajectory would be into the page in this region, and then it would have to come back out. So it's almost as if it's a circle that's going into and coming out of the page. Now, it's not completely perpendicular. So that means now that there's a component of its velocity right here, the parallel component of the velocity, that will continue to drive it forward, or in other words, it will have momentum moving forward. So it will actually spiral through the magnetic field. The magnetic force is causing the turning, but the initial velocity that it had that's parallel to the field and not being affected by the field will actually drive it forward. You can think of this in sort of a similar way or an analogous way to the gravitational force. We know that the gravitational force affects the particles or an object's acceleration only vertically. So we see that it's changing its speed vertically, but not horizontally. Now the analogy here is that the magnetic force is only acting centripetally, but is not acting in the parallel dimension. Thus we would have a momentum moving forward, and we would call this pattern a helical path. So to end this video, I'm going to present you a challenge that will be answered in the next one. Do you think it's possible to have a charged particle, let's say a positively charged particle, move through this magnetic field, but not helix as it moves? In other words, is it possible to move it in a straight line at a constant velocity? The answer is yes, and the hint is you need to also use an electric field to do this at the same time. So I'll leave you there trying to determine how you would have to set up a magnetic and electric field in order to keep a positively charged particle moving in a straight line at a constant velocity. Then, in the next video, I'll present the answer and spend some time comparing and contrasting the electric and magnetic fields.